Hi everyone, thanks for checking out this video. So I'm actually making this video in response to a comment I got from one of my viewers. So I had previously made a video showing how to implement the SIR model in Python, doing a deterministic implementation with like the differential equations and stuff. But someone left a comment on that video asking to see a stochastic implementation of this model. So that's what I'm going to do with this video. I'm going to show you guys how to implement a stochastic simulation of the SIR model in Python. Okay, so before we get into the math and the code, I'll just give you guys like a quick review of this model. So the SIR model is a commonly used model in epidemiology that tries to explain how an infectious disease can spread through a population. And it's a very simple model. It makes a lot of simplifying assumptions that actually don't apply to a lot of diseases in real life. But it can be at least a good starting point, at least kind of a good like jumping off point for studying an infectious disease. So basically the model has three compartments, and the S, I, and R each stand for one of the compartments that the people in this population could fall into. So you have the people who are susceptible. That means they haven't encountered the disease yet, so they're susceptible and can be infected by the disease. You have the infected people. Those are people who currently have the disease and can spread it to others. And then you have recovered people. And those are the people that have recovered from the disease. And after you've recovered, you can't catch the disease again. You may also see the R stand for removed. That's another way I've seen the model could be recovered or removed. I think removed is kind of implying that like someone could have either recovered or died from the disease. But I'm trying to be a bit optimistic with my video here, so I'm just calling it recovered, just assuming that everyone who gets the disease eventually recovers from it. And the population moves through the compartments only in this direction. You start off susceptible, and then you become infected, and then you become recovered. There's no moving backwards through the compartments. So again, it's a very simple model, makes a lot of simplifying assumptions. But even though it's a pretty simple model, it's also like the basis for a lot of more complex models. So you may see more complex models in epidemiology that are kind of based on this foundation, but maybe have some other dynamics going on. Like maybe you can become recovered, but then still be infected, but with like a lesser rate of infection or something. But a lot of more complex epidemiology models are still kind of based on this general foundation. Okay, so that's kind of a basic introduction. So now let's take a look at some of the math. Okay, so this is the deterministic version of the model here. We have three ODEs, one for each one of our compartments that we're keeping track of. There's the susceptible compartment here, infected, and then recovered. And we also have this this variable n, which is just keeping track of the total population level. This is going to stay the same throughout, so I just kind of wrote that at each time point it's just the sum of all the compartments. But this could even just be like a static parameter too, because no one's entering or leaving the population. So this could even just be like a constant parameter. But here I've just said that it's at each time point it's just the sum of all the compartments. But yeah, n is just the total population number. So I know the math here might look a little bit confusing at first, but it's actually not so complicated. So this term here is just the term expressing like the rate at which sensitive people become infected. And we have this parameter beta here. That's just some constant parameter that we use to determine like the rate at which the infections are happening to sensitive people. So we have this constant parameter beta here. So that's just kind of what we use to determine the rate at which susceptible people can become infected. And then this whole rate, though, actually depends on this parameter beta, as well as the current level of the infected population, as well as the current level of the susceptible population. So the more susceptible people you have, the more chance there is for some of them to become infected. And also, since it's spread by infected people, the more infected people you have, the more chance there is for susceptible people to become infected. And then this other term we have here is used to explain infected people becoming recovered. So we have this constant parameter gamma here. This is the rate at which infected people become recovered, and then that's just multiplied by the current number of infected people. So yeah, really only two terms here: susceptible people becoming infected and infected people becoming recovered. And we have two constant parameters, beta and gamma. And just as like a little side note here, you guys may hear about this thing called R naught. This is like the basic reproduction number of the disease. So basically, we can talk about this thing called R naught, which in this model is our parameter beta divided by our parameter gamma. And this is just the expected number of new infections that will be generated by each existing infection. So like if a person becomes infected, what's the expected number of new people that they'll infect? So yeah, we can express that in terms of our parameters beta and gamma. So yeah, this is the deterministic version of the model. This is what I previously made a video about, but our goal in this video is to make a stochastic implementation. So in order to do a stochastic model, if you guys have watched my previous videos, you may be kind of expecting this already. But for the stochastic model, we basically need, we always have to do the same thing, where we break the model down into events and propensities. So, yeah, deterministic models, we can talk about like ODEs and simulating these ODEs. For a stochastic model, we're going to use the Gillespie stochastic simulation algorithm, and we need one of these events tables. So we need this table that talks about events that can happen and the propensity of each event. So it's kind of like we mentioned before, there's really two events that can happen. The first event is a susceptible person becoming infected. And for that, we list this event here, but we list the event in terms of the updates we're going to be making on our compartments. So when this event happens here, a susceptible person becoming infected, we have to update our susceptible variable by decreasing it by 1. And then the infected variable increases by 1. That's just how we model the susceptible person leaving the susceptible compartment and entering the infected compartment. And the propensity here is just basically the same as this term in the deterministic model. It's beta times the current infected level times the current susceptible level. All of that divided by the total population level. So we're getting that directly from the deterministic model. And the second event that can happen is an infected person becoming recovered. So when that event happens, we update our infected compartment by decreasing it by 1, and we update our recovered compartment by increasing it by 1. And the propensity of that event is gamma times the current infected level. So yeah, once we have this event propensity table, we have enough to write a Gillespie stochastic simulation of this model. So I'm going to show you guys how to write the Python code for that now. So we're going to start by just importing some of our usual libraries. We're going to import numpy as np, import matplotlib.pyplot so that we can plot our results, import random, and import ODE int from scipy.integrate. That's just so we can also plot the deterministic results to compare to our stochastic results later. I'm going to be rushing through this a bit because I'm kind of assuming that if you guys are watching this, you've already seen my basic video on the Gillespie algorithm. So if you guys haven't yet seen that, if you guys are confused by any of this Gillespie algorithm, I'm also going to link you guys in the description to this original video I made on the Gillespie algorithm, kind of explaining the basics and explaining kind of more in depth about this stochastic simulation algorithm. But yeah, kind of assuming you guys have already seen that at this point. So I'm going to kind of rush through this a bit, but I'll try to still explain what's going on too. So basically, we're going to keep track of each one of our variables by defining a list. So we're going to define a list of the susceptible variable. Going to start that off at 100, and then the way it's going to work in this simulation is that we're going to run the simulation, and then as the compartments get updated, we're going to be appending the new values to these lists. So as this gets updated, we might be appending like the new values like this here. But we're just going to start it off with the initial value. Start with 100 susceptible people, and then we'll start with 1 infected person. Keep in mind, in order to have this simulation make sense, you need at least 1 infected person, because infections can only happen resulting from infected people. So if you start with 0 infected people, then nobody else will get infected. So we're going to start with 1 infected person, and we're going to start with 0 recovered people. And we're also keeping track of the time with another list. So we're going to start at time point 0. But as we run the simulation, we're going to be updating these new time points, and then updating the values of these variables by appending to these lists. Okay, so let's define a endpoint for our simulation. We're going to end it at time point 500. I'm keeping the time points unit list now, just kind of showing you guys how to write the code. I'm not necessarily trying to make it super realistic. But you guys could maybe think of this as like 500 days or something. But yeah, just keeping this kind of unit list for now. I'm going to define some values for our parameters. So I'm going to make beta 0.04 and gamma 0.01. And if you guys are just kind of thinking about this gives us a R naught of 4 because it's beta divided by gamma. So that means for each new case, the expected number of new infections resulting from a new case is 4. Okay, so the way we do the Gillespie simulation is we're going to have a while loop, and we're going to say while the most recent time point is less than t end, we're going to run our simulation. And then so once the most recent time point in the simulation is greater than or equal to t end, we'll then end the simulation because we've reached the stopping time point. But okay, so as long as the most recent time point is less than our end point, we're going to keep iterating through this while loop and keep running the simulation. So the first thing we do is we say n equals the most recent value of s plus the most recent value of of I plus the most recent value of R. And like I said, like the population is the same throughout. No one is entering or leaving, so we could even put this outside of the for loop. We could even just make this, because it's always going to be 101. We don't actually have to update it every single time. But just for now, I am going to leave it in the while loop just because I think it's good. It's good for building intuition, because in a lot of other models, you will have to update this every time, every iteration. And then we're going to put all of our propensities in a list. So it's just these two propensities here that are the propensities of each one of these events happening. So I'm going to call this the props list. And then the first propensity is beta times the most recent value of I times the most recent value of S, all of that divided by N. And so I just copied that directly from this propensity event table we have here. Just copy that directly into this propensity list. But again, making sure we're updating with the new values of I and S each iteration. And then the second event propensity is just gamma times the most recent value of I. Okay, so that's the propensity list we have here. The next thing we're going to do is calculate the sum of both of these propensities. So I'm going to call this prop sum, and this is just going to equal sum of the props. Okay, so the next point here, and I guess I should have quickly explained this too, even though, again, I'm assuming you guys have already seen my introductory video on the Gillespie algorithm, but just to review a bit, like with the Gillespie algorithm, each one of these iterations in this while loop, we're going to be randomly choosing two things. So first, we randomly choose the time point when the next event is going to happen, and then the second thing we choose is which event that's going to be. And we choose both of these things based on these event propensities that are updating every time with the most recent values of the variables. But yeah, based on these event propensities, we choose the next time point of the next event, and then we choose which event that will be. And both of these are random choices we're making. So yeah, first we're going to choose the time point of the next event. So we're just going to take a random draw from an exponential distribution. Going to do this with numpy.random.exponential. And we're going to set the scale of this to be 1 over the prop sum. Again, if you guys are curious in like the theory of why we're doing this, I'm going to refer you guys to my introductory video on the Gillespie algorithm. But for now, assuming you guys are kind of familiar with that, yeah, we're just defining like basically the interval from the current time point to the next time point of the next event. That's going to be drawn from a random distribution that depends on the sum of the propensities of these events that could be happening. Yeah, so tau is basically going to be this random interval from the last event time point to the next event time point. So then after we select this random draw tau, we're just going to say t dot append the last time point plus tau. So that's telling us that the time point of the next event occurring is going to be the time point of the last event plus this random interval tau that we just drew from this exponential distribution. Okay, so that's the first part of the Gillespie algorithm here, is just choosing which what the time point of the next event will be. And then the second part is choosing which event is going to be happening. So to do this, we're going to take a random draw from a uniform distribution between 0 and 1. A random uniform variable between 0, and 1. And then based on where this random number falls, we're going to choose which of the events is going to happen. So I'm actually going to copy and paste a little bit here, but we're basically checking where this random number falls in relation to the current values of these propensities. So if this random number multiplied by the sum of the propensities is less than the current value of the first propensity, then we choose for this first event to happen. And if that event happens, we update each variable accordingly based on these compartment updates. So if this first event happens and a susceptible person becomes infected, we just update the susceptible variable by decreasing the last value of it by 1, and we update the infected variable by increasing the last value of it by 1, and then we make no change to the recovered variable, but we still append to the list. We basically want one item in this list for each time point. So every iteration of the while loop, we append a new number to each one of these lists, even if this new number is the same as the previous level of the variable. But yeah, so basically, we're just deciding which one of these events is going to happen based on this random number between 0 and 1 multiplied by the prop sum, and then seeing where this falls relative to the current values of the propensities. So if this if statement resolves to be false, then we know that it's not the first event happening. So in this case, it must be the second event happening. It must be that an infected person is becoming recovered. Here, I kind of wrote this out. I wrote it out like this because if you had like more than two possible events, then you'd be writing it like this. But actually, you know what? Just to not confuse you guys for now, I will just comment this out and call it else, because in this case, we only have two events, so we know if the first event isn't happening, that means it must be the second event. But I will leave this commented here because this is the kind of syntax you would use if you had like 3 or 4 or 5 possible events and you have to go through with elif statements and like check each one of them. But for now, we only have 2 events, so we know if the first event isn't happening, it must be the second event. And if this second event is happening, again, we just update the variables accordingly. So we append to the I variable the previous value decreased by 1, and we append to the R variable the previous value increased by 1, and then we append to the S variable just the previous value not changing, but we do still need to append something to just make sure that the lengths of all these lists are all the same. Okay, so this is really all there is to the Gillespie algorithm. So this while loop is just going to iterate through and just keep running through this until the most recent time point hits this endpoint. Although there actually is one more thing we do need to add here, because there is a way that you can get an error here. If you run out of recovered and infected people before you reach T end, then you're just going to get an error because it's going to be trying to see what the propensities are, but no events can happen, but you'll still not be at T end. So I actually am going to add this other condition here, which will be so this condition here is just saying that we still have either some susceptible people or some infected people. Basically, if we don't have this condition, I mean, you guys can try this out yourself. Like, sometimes it's still going to run okay, but there's going to be other times where everyone gets infected and recovers before you reach T end, and then you just get an error because the simulation doesn't know what to do because there's no more events that can happen. Even adding in this condition, there's actually still a rare situation where you may still get an error. And basically that rare situation is if our starting person becomes recovered without infecting anybody, then you're going to have that same situation where you're going to get an error because we're going to not have reached T end yet, but there's going to be no events that can happen because all we have is a bunch of susceptible people and one recovered person. Yeah, that's going to be pretty rare, so I'm just going to kind of leave that out for now. I mean, you still may get an error every once in a while because of that, but I think for now it's fine to just be okay with that error when it like rarely comes up. Actually, we do need something else here. I kind of made a mistake. This should actually be greater than or equal to 1, not just greater than 1. But yeah, okay. Yeah, with that, I think we're basically done with the simulation. Now, what we want to do is just plot these results. So I'm actually just going to copy and paste in, being a bit lazy here, just copy and paste some of this plotting code so we can plot our results. But yeah, let's give this a run and hopefully it'll work okay. Okay, so here's our stochastic curve results here. Just plotted one for each one of our compartments. Yeah, looks pretty much like what I was expecting. We have our susceptible people. This can only go down. Susceptible people can only become infected. So this goes down over time. Over time, the number of infected people at first increases and then decreases as they recover. And the number of recovered people can only increase over time. So one last thing I want to do is I want to show you guys how this plot compares to the deterministic model. So again, I'm going to be a bit lazy and just copy and paste in a bunch of stuff here. But yeah, this is stuff that I'm just copying and pasting in from my previous video on the deterministic model. So I encourage you guys to check that out if you're wondering where this code's coming from. But yeah, this is just going to be a plot of the deterministic results, and we're going to see how the stochastic results compare. So yeah, just copy copy and paste this all in here. And yeah, let's give it a run. Oh, you know what? It actually did happen that with this run of the model, I actually did get this error I was talking about. So basically, this error after we've put in this condition, like I'm basically getting this error because the infected person, yeah, they recovered before they could infect anybody. And you guys may see that happening sometimes. I mean, I guess I shouldn't have said that it was super rare. It's actually not that rare. I mean, it could happen the way we've set things up. Yeah, like this infected person could just recover before they infect anybody, and then we just get this error because the model just like no events can happen. But yeah, just I mean, if you guys are working on like an academic project, you may want to like error proof your model so that this can happen. But for now, I'm just gonna say okay to this error and just run it again. So I'm just gonna run until that doesn't happen, basically. Yeah, so here it is. We have these smooth curves here that are our deterministic curves, and then we have the stochastic model results here. You can see they kind of follow the deterministic ones. This was a nice run of the model. If you run it again, it may look like it's different. You can kind of play around with it, run it a couple times. Sometimes it might come out looking pretty nice like this, like a very nice match. Other times it might look like it's different. That doesn't mean you did anything wrong. It could just be the stochastic nature of the model. You know, you run it multiple times, you get like multiple different results. Sometimes it looks like a nice match, sometimes it doesn't. But if you run enough of them, like on average, they should kind of look like a pretty close match to the deterministic model. That's actually a good way to do like a sanity check here. Make sure you don't have any errors in your stochastic model is by checking to make sure that at least on average it should kind of match these deterministic curves like pretty nicely. But yeah, that's all I have for you guys for today. If anyone has any questions, just let me know in the comments and I'll try to answer them. Also, all of the code for this is going to be up on my GitHub, which I'll link to in the description. So if you want to try it out yourself, I'll put the code up there if you want to give it a try. But yeah, thanks for watching and just let me know if you have any questions and see you guys next time.